So good afternoon. We're going to try to do a little bit of a lesson on factoring polynomials. So if you recall last time we were talking about multiplying polynomials. Multiplying polynomials, we were given the factors and we multiplied them out to get the product. So if you recall, when we had 3 times 5 equals 15, that 3 and this 5 were called the factors and the 15 was called the product. In factoring, what's going to happen is we're going to give you the product and we want you to find its factors. So as we move through this, a good organizer for this is what we call big T. So let's find all the factors of 18. And big T, the way we do this is it organizes them as factor pairs. Now to find factors, division can be used. The factors that we want are whole numbers, not decimals. So we don't want any decimals. Feel free to use the multiplication chart that we had in class, or if you want to download one from the internet, that's fine, or just use your calculator. And remember, if you use your calculator, no decimals when we do that. Just recall that if I give you 2 times 9 equals 18, inversely means to go the other direction. I can say 18 divided by 9 is equal to 2. Now, similarly, if I give you, what number times 3 is equal to 18, I can go backwards and say, well, 18 divided by 3 must give me that missing factor. That's how division can be used to find the missing factor. And of course, that would be 6. So as we do our factor pairs, 1 times 18 would actually be the first pair that I would want. And then we'd have 2 times 9 would be my next pair. 3 times 6 would be my next pair. Notice that 4 is not a factor because 4 times, there's not another number there that would give me this, it does not divide into it evenly. It gives me a decimal. So 4 is out. Also, 5 is not a factor of 18 because you can't multiply by 5 by a whole number to get that. So again, we're wanting these whole numbers at this point. After 5 comes 6. Notice that 6 times 3 is 18, but that's just repeating. So really, our only factors of 18 would be 1, 2, 3, 6, 9, and 18. Now, let's list the factors of 24. If you want to pause the video for a second, we can do that. So the factors of 24 would be 1 and 24, 2 and 12, 3 times 8, 4 times 6. 5 doesn't work. 6 times 4, 6 times 4 would, and that would be repeating. So that would be my factors of 24. Something else to pick up on is the divisibility rules. Remember, any even number is divisible by 2, which means 2 is a factor of any even number. Also, if a number ends in 5 or 0, that means that number is divisible by 5, which means 5 is a factor of any number that ends in a 5 or a 0. So the greatest common factor, I'm going to be using this GCF from here on out. It's going to be the largest common factor. So if I want to find the greatest common factor for 18 and 24, if I look up here, notice how we have several different factors. So if I circle those, so notice how we have a 1, a 2. Notice how a 1 and a 1 are common. A 2 and a 2 are common. A 3 and a 3 are common. But notice that 6 is the largest common factor between an 18 and a 24. So as I move forward in this, we see that 6 would have been the greatest common factor of that. So the GCF for 18 and 24 would have been the 6. Another thing we want to bring up to your attention this time is what we call prime numbers. Prime numbers have exactly two factors, one in itself. The first 5 prime numbers are, well, let's start with just the number 1. 1 times 1 would be 1, but notice that that's not two different factors. When I say two factors, I mean two different factors. So 1 actually has one factor to get that. It's the same factor. But if I go to 2, notice that 2 does meet the characteristics of a prime number. 1 times 2 is the only way to get a 2. So it's 1 and itself. So 2 would be a prime number. If I move on, we would see that 3 would also be a prime number. 1 times 3 would be the only two factors to get that. If I look at 4, we do have 1 times 4, but notice we also have 2 times 2. That's actually 3 different factors. So 4 is not prime. So if you want to pause here, let's see if you can find the other 3 factors of that we want to look for, the first 5 prime numbers. So 5 would be the next prime number because 1 times 5 is the only pair, 1 in itself. 6 is not prime, but we do have 1 and 6, but we also have 2 and 3. That's 4 different factors. 7, yeah, 7 would be prime, 1 times 7. 8, 1 times 8, yes, but 2 times 4, that's 4 different factors. 9, we have 1 times 9, but we also have 3 times 3. So that's actually 3 different factors. 10, no. 11, yeah. 11 would be our 5th prime number that we want to find. Now, that's just the first 5 prime numbers. There are many, many prime numbers to be looking for. So, prime numbers can also be used to rewrite a number as a product of prime numbers. When we do this, this is called a prime factorization. Again, a great organizer is the big T. So keep that in mind. Big T is a great organizer there. Ignore that D there. So again, when we rewrite 18 and 24 as a prime factorization, we're going to go backwards again. So again, this is more of a division strategy. So I'm going to start with the number 2, and I'm going to ask myself, does 2 go into 18? Yeah. So 18 divided by 2 would be a 9. So that means we pulled the factor of 2 out. Now we're left with this 9 as a factor. But notice that 9 is not prime, so we have to break it down. 2 doesn't go into it, but we do remember that 3 goes into 9 3 times. And we do know that 3 goes into 3 one time, and since 3 is a prime number anyway. So we kind of got that going on there. So if you notice there then, we have, this is my prime factorization, this part over here. So that means that, 2 times 3 squared would be my prime factorization, or we can write that as 2 times 3 times 3. Looking at 24, notice how, again, if you want to pause the video and see if you can come up with those prime numbers using 2, 3, 5, 7, 11, that'd be great. So 2 does go into 24 12 times, so that means I've taken out or divided a 2 out. Now I'm left with a 12. But since 12 is not prime, we want to break it down. And 2 does go into 12, and that leaves me a 6. And 2 goes into 6, and that leaves me a 3. And we know that 2 doesn't work there, but 3 goes into 3 one time. So again, the prime factorization is this left side over here. So this is my prime factorization, is that product of prime numbers. So if I want to write the prime factorization, we should have then 2 to the third times 3, or in other words, that still just means 2 times 2 times 2 times 3. So to find the greatest common factor here, all we really got to do is circle what's in common. So what's in common, notice how we have a 2 here, and we have a 2 here. But that's only number 2s we have in common is just 1, 2. When it comes to 3s, we have 2 3s here, but only have 1 3 there. So notice that we only have 1 3 in common. So we have that pulled out. So our GCF becomes then the factors that are in common, which would just be that 2 times 3, and that would also give us that 6. So if we just list the factors of each number, we can see that the largest one is 6. Or if we do a prime factorization and identify the common factors, that's another way to identify the GCF. So see if we can move into the next page here. So as we move into this page here, we see that we want to find the GCF of 8x squared and 6x. To do this, there's several ways again. One is just doing it mentally, but basically what I'm going to do is just remember the GCF is going to be a product of common factors. The way I'm going to do this the first time is I'm just going to focus on the 8 and 6, and I'm going to find the greatest common divisor, if you will, or greatest common factor by using what we call factor pairs. So again, I'm going to use that with big T. So again, the greatest common factor or greatest common divisor, because we are using division here to find the factors. So 1 and 8 would be a pair of factors. 2 and 4 would be a pair of factors. 3 doesn't work. 4 and 2 does, but that's just repeating. So 1, 2, 4, and 8 are my different factors for 8. For 6, we're going to have 1 and 6. We're going to have 2 times 3 is also 6. And 3 and 2 would just be repeating. So we just have those 4 different factors. So if I look at that, we kind of see that 2 is the largest common factor. 1 is a common factor, but 2 is the largest. So from here, 8 and 6 have 2 as a GCF. Now, how many x's are in common with 8x squared and 8 and 6x? So remember, x squared really means x times x. And we have an x here. So again, how many do we have in common? So notice how we have an x here, and we have x here, but that's all we have in common is just 1x. So they just have 1x in common. So when it comes to an 8x squared and a 6x, we just have 1x in common. So it's actually the fewest in common in that sense. It's actually not 2, but 1, if you will. So it's got to be in common, and they only have 1x in common. Because sometimes this word greatest throws people off, but it's got to be common as well. So the GCF basically means we put these two together. So the 2 and x come together, and my GCF would actually be just 2x or 2 times x, if you will. Now, another way to do this is I could also do this with respect to the prime factorization. So if I do 8 using a prime factorization, that means I want to write it as a product of prime numbers. We would see that we have 2 does go into 8 4 times, 2 does go into 4 twice, and 2 goes into 2 1 time. So 8's actually just a bunch of 2's. 6, 2 does go into 6 3 times, but 2 does not go into 3, but 3 does go into 3 1 time. And since 2 and 3 are your prime numbers there, we're good to go. So what I can do here is I can rewrite 8 then as 2 times 2 times 2, and then I have this times x, if you will. And then this 6 is going to be 2 times 3 times x. So using this strategy, all we have to do is circle our common factors. So notice how they have a 2 in common, but they don't have a 3 in common. They have an x in common, but they only have one x in common. So if I put that together, we see by circling those common factors, we have 2x as our GCF. So 2x is the greatest common factor between those two monomials. So if I want to find the GCF for 12x and 9, again, there's several ways of doing it. Here, I'm just going to show you the factor pairs strategy to start with. So again, the factor pairs really just goes with the actual numbers. So we have this 12 and this 9. So I'm going to use big T as an organizer. So we have 1 times 12 is 12, if I'm doing factor pairs. 2 times 6 is 12. 3 times 4 is 12. 4 times 3, 4 times 3. That's just repeating. So that's off the table. We don't need it. If I do 9, we do have 1 times 9 and just 3 times 3. But notice that 3 there is repeating, so that means we get to stop. So our factor pairs here, we have a 1, 2, 3, 4, 6, and 12 as the different factors of 12, and 1, 3, 9 are the different factors of 9. Notice how they do have a 1 in common. They don't have a 2 in common. They have a 3 in common, but that looks like the biggest. As far as the x's go, this has an x and this doesn't have an x. So the GCF here is going to equal then this 3. If I'm doing a prime factorization of 12x and 9, again, I can use big T here. So again, our prime numbers, 2 goes into 12 6 times, 2 goes into 6 3 times, 2 doesn't go into 3, but 3 goes into 3 1 time. So our prime factorization is this 2 times 2 times 3. For the 9, 2 doesn't go into 9, 3 goes into 9 3 times, and 3 goes into 3 1 time. So again, 3 times 3 is my prime factorization. So remember, the prime factorization is just this left side. So if I'm using big T, it's just this left side here. So based on that, what we're looking for are our common factors. So they don't have any 2's in common, but this has a 3 and this has a 3. So the only thing in common would be a 3. As far as the x's go, again, there aren't any x's in common. So again, the GCF is just going to be this 3 using the prime factorization. So they get you to the same spot. So where this takes us to then is another topic that we need to bring to your attention is what we call rational numbers. So rational numbers is something moving forward that we'll hear more about. So rational numbers is any number that can be represented as a fraction. So if I look at whole numbers, if I look at, say, the number 3, can I write 3 as a fraction? Well, actually, I can by writing that as 3 over 1. So whole numbers are also called rational numbers since they can be expressed as fractions. If I look at the number 5, of course, we can do again 5 over 1. But remember, we can do anything. We can also use maybe like 15 over 3. That's still a fraction, but it simplifies down to 5. So since I can express 5 as a fraction, 5 is called a rational number. When it comes to fractions, though, 1 is a special fraction. So 1, notice if I have a 2 on the top, if I put a 2 on the bottom, 2 over 2 represents 1, because remember, this means 2 divided by 2, which would also represent 1 whole, or 1. Notice how if I have a 7 on the bottom, to keep that equal to 1, I have to put a 7 on the top. So if the numerator and the denominator are the same, that means we're talking about something that equals 1. So if I have the variable x on the top, to make it equal to 1, I just got to put the variable x on the bottom, and now it's equal to 1. So something else to bring to your attention is decimals can also be written as fractions, which means decimals are also called rational numbers. So moving forward, we're probably going to see a little bit more decimal math as well. Now the reason 2/10 is a fraction is because, like I said, this reads as 2/10. Notice how there's a 2 there, and since it's in the tenths place, this reads as 2/10. And so 2/10 as a fraction, 2/10 as a decimal, they read the same way. But as a fraction, we can also reduce that down to 1/5. So 1/5 is the same thing as 0.2 as a decimal. Notice how we have 0.25, but if I'm reading it, notice how this goes 2 decimal places. So this actually goes out to the hundredths place. So this reads as 25 hundredths. And 25 hundredths is the same thing as 1/4. So 0.25 or 25 hundredths is the same thing as 1/4. So something else we want to mention here is you can multiply a fraction by this special one. The fraction is going to look different, but it's still going to have the same value. For instance, if I have 1/2 here, if I multiply the top and the bottom by the same number, say if I multiply the top by 3 and the bottom by 3, 1 times 3 is 3, 2 times 3 is 6. 3/6 looks different, but it's still the same thing as 1/2, just in what we call higher terms. So if I have this 2/3, I can multiply it by a 5. But if I multiply the numerator by 5, I got to multiply the bottom by 5 to keep this special 1 here. And when you multiply by 1, it doesn't change the value. When I do it this way, it just changes its looks. So 2 times 5 is going to be 10, and 3 times 5 would be 15. So 10/15 would be the result. Something else we want to talk about with fractions is 3/4. Back in the day, 3/4 was modeled using a rectangle. So if you want to pause the video, could you draw a rectangle and show 3/4? So to show 3/4, what you actually do is divide the rectangle into 4 pieces to start with. It doesn't matter how you divide it, as long as they are equal pieces. So I'm going to do it that way. And the numerator then tells me I have to shade 3 of those. So from a picture perspective, 3/4 looks like that. It's a whole cut into 4 pieces, and then you get to take 3 of those 4 pieces. For us, 3/4 means 3 times 1/4, or 3 1/4, which also means a fourth and a fourth and a fourth. So 3/4 is the simplest way to express this notation. Drawings are busy. This is too much writing. This isn't bad, but this is even quicker. So 3/4 really means 3 1/4. So if I understand that logic, when it comes to 3/5 and 2/5, what this basically is asking is how many fifths are present. So we have 3/5 and 2/5. Notice that would be 5/5. 5/5 are present. And therefore, the answer would be 1/2. So what I pick up on is when it comes to adding fractions, the denominators must stay the same. And then what you actually add are the numerators. So keep that in mind that the denominators have to be the same. And when you work it out, you have to add the numerators and you have to keep that denominator the same. But when I look at this problem right here, notice I have 3a plus 5/6. I can't work this problem out because I do not have the same denominator. And that's what has to be true to add fractions. So what I'm going to do here is I'm going to use a prime factorization and rewrite the denominators. So this is going to be 3. And remember the prime factorization for 8 is going to be 2 times 2 times 2. Plus then this 5/6, I'm going to write the 6 as a prime factorization. So it's going to be 2 times 3. So those prime numbers would give me 6. So if you need big T, you can use big T, but if you start to do enough of this, you start to remember what we're doing. Now, to have a common denominator means we have to have the same numbers on the bottom. So notice how if I have 3 2's over here, I have to have the same number of 2's over here to have the same common denominator. So if I multiply the bottom by 2 2's, remember you got to multiply the numerator by 2 2's to keep it equivalent. There's that special 1. Notice how this has 3 2's and this now has 3 2's. But notice how this has got a 3 and this one doesn't. So you got to multiply this over here by 3. But when you do that, you have to also keep it equal by multiplying the top by 3. So the fractions are going to change looks, but they're going to be equivalent. So what this boils down to then is you have 9 over 24, if I work it all out. And you're going to have 20 over 24. So now I can actually add these together. I would have 29 24ths. So that's how you would be adding those fractions. So this brings us to the next slide. Let's make sure I've got it right here. Yeah, we're on the right slide. So this brings us to our next slide. So when we do this problem right here, again, we're going to start now. If you notice, looking through here, we're going to have what we call polynomials. So the first thing when it comes to factoring polynomials is we want to express this as a multiplication problem. So right now what we have is the product, and what we need to do is write it as a product of factors. So this is called a factorization, if you will. And remember, when we work with polynomials, multiplication was modeled using um, parentheses. So the way we do this is, if I want to factor this polynomial, we want to find the greatest common factor. Notice that, what we're focusing on is this is the first term and this is the second term. What we're looking for is a common factor. So remember, if I rewrite this, 5x it can't be broken down because 5 is prime. But notice that 15 can be written as 3 times 5. So if I use the prime factorization strategy. So if you notice here, from there, we're looking for common factors. Notice how they both do have a 5 in common. So what we do in factoring polynomials is once we find the greatest common factor, which is 5, we're going to write the GCF out in front. So the 5 goes out in front, and then we're going to use parentheses, and what's left is going to stay inside the parentheses. So the x plus 3 would be what's left. So notice that, basically this could be done mentally. If I look at 5x and 15, I'm looking for the GCF between a 5x and a 15. If you recognize that 5 is the biggest factor, we pull that out. And if you pull that out, that leaves us just the x. And again, when we pull out, that means you're dividing. So if I take a 5 out of this, in other words, if I divide that 15 by 5, that's going to leave me a 3. And so that would become the factorization of 5x plus 15. It turns into a product of factors. So those factors would be the 5 and the x plus 3. So if I'm looking at this next example, 3x minus 27. Again, the 3 we probably don't need this t for an organizer because 3 does go into 3 one time. So in other words, 3 is a prime number. So that didn't really go very far. Now the 27, you may not be as familiar with it. So if I want to do a prime factorization of 27, 3 is going to go into 27 9 times. 3 is going to go into 9 3 times, and 3 is going to go into 3 one time. So 27 really is 3 3s. So I can write this as 3 times x minus then 3 times 3 times 3. So if I want to find the common factor, GCF if you will, we see that they do have a 3 in common. So I'm allowed to pull that out. And then what we do is just put together what's left. So as we do this, we pull the 3 out. We have x minus 3. And notice how I set up here, simplify. We want to go ahead and clean up this 3 times 3. 3 times 3 is actually 9. So if you want to do it mentally, hey, what does a 3 and a 27 have in common? They have a 3 in common. So if you pull a 3 out, that leaves me a 3 out, and that leaves me just the x. If you pull a 3 out of 27, 27 divided by 3 would be a 9. And that's what it would look like if you want to do it mentally. If you're not good with mentaling, then, the prime factorization is a good organizer to make that happen. As we move forward, we're going to get into some more vocabulary, factoring polynomials. So a second degree term, that's going to be called the quadratic term. The first degree term is going to be called the linear term. And the 0 degree term, of course, is called the constant. So as we move through this, notice how we have this x squared here. That's now going to be called the quadratic term. We have this bx. Notice how the exponent of the x is actually a 1. So therefore, this is called the linear term. And then the n, notice how there's not an x there because its exponent was 0. Remember, x to 0 is 1, so we don't even show it. So the constant is going to be the number that does not have a variable with it. So quadratic term, linear term, and constant, we're going to be using a little bit of that language. So if we have polynomials that look like this, notice how the coefficient of the x squared term, the quadratic term, is 1. These are going to be not too bad to do. So what I'm going to do first is organize this using what we call foursquare. Now, if you remember, in multiplying x plus 8 times x plus 2, the x and the 8, they went on the edges. So the x and the 8 were on the edges, and the x and 2 were the edges. So if I gave you the factors using foursquare, the product was on the inside. So this x squared would go here, this 2x goes here, this 8x goes here, and this 16 would come here. If I put this all together, we have this x squared plus this 10x plus this 16. That's what we did in the last section. So notice how if we have this, we're going to have this quadratic term, this linear term, and this constant. Notice they're going to be on the inside of the rectangle of foursquare. What we're going to be looking for is the factorization, which is going to be the edges. So again, the product of the polynomial is going to be on the inside, and the factors are the edges. So that's what we have to pay attention to as we move forward. So what we want to do here is we want to factor x squared plus 9x plus 8 using what's called foursquare. So if you recall, the quadratic term was located in the top left. So when I use foursquare, the quadratic term is going to be on the inside. It's going to be in the top left. Something else we noticed was the constant was in the bottom right. So the 8 is going to be located here. So it's going to organize part of the math. What we have to do is figure out what goes here and here. What happens is the factors of the constant, which is this 8, must add up to equal the coefficient of the linear term, which is this 9. So what we pick up on is in using foursquare, we also can use big T. And here I'm going to use what we call factor pairs. So I have this 8 here. So the factor pairs must multiply to equal the 8. And they must add up to equal the 9. So when I do this, basically what I'm doing is I'm breaking apart the 8 into its factor pairs. So I'm going to have this 1 and 8, 2 and 4, 3 isn't going to work, 4 and 2. So notice there really isn't a whole lot of pairs here. But the catch is I want to add up to this 9. So there's two things that have to pass. I have two factor pairs, but which pair actually adds up to 9? So what we see here is that 1 and 8 actually give me the 9. So what we're going to do is the factor pair that works, that becomes the coefficient of linear terms, is what we're looking for. So it's actually coefficient of the linear term. So the factor pair that works becomes the coefficient of the linear term. So notice how the 1 and 8 became the coefficient of the linear term. Okay. So what we're going to do, we're going to replace these two pieces here with the coefficients. So that's, I guess, what I meant by coefficients as linear terms. So this 1x and this 8x will go here and here. So they become the coefficients of the linear term. Once we do that, we now have the inside built. So this 1 and 8 become the coefficients of the linear terms. Now, what we want to do is we want to build the edges. So what I do is I just start here. X times x is the only way to get x squared. X times 1 is the only way to get that 1x. 8 times x is the only way to get this 8x. And 8 times 1 does give me 8. So that we started with this, we broke it into this 4 square pieces, and now we got out to our edges, which is actually the factorization. So x plus 1 and this x plus 8 would be my factorization. And again, it doesn't matter what order you put those in. So when I want to factor this polynomial using 4 square, what we pick up on is the quadratic term goes in the top left. The constant goes in the bottom right. Now, what we need here is we need to build these two linear terms. And how we do that is the factors of the 21, and I'm going to use big T for that, they must add together to give me this negative 10. So we're going to start with big T and find the factors of 21. So 1 and 21. 2 doesn't go into 21. 3 does go into 21 7 times. 4 doesn't. 5 doesn't. 6 doesn't. 7 does. That's repeating. So luckily we only have 2 different factor pairs. But which one has the potential of giving me a negative 10? It looks like this 3 and 7, but to be a negative 10, they're both going to have to be negative. If I change them both to negative, I still got to get this 21. Does a negative times a negative still represent a positive? And we know that yes, when you multiply two negative numbers together, it does give you a positive. So these are going to be the coefficients of my my middle term, negative 3x and this negative 7x. So we do have these two linear terms here now. Once I do that, we now work on the edges, and this is where our answer is going to be located at. So x and x, again, if you want to pause to finish the rest of this, you can. So x times negative 3 would be negative 3x. I'm going to have negative 7 times x is going to be negative 7x. And negative 7 times negative 3 does give me my 21. So the factorization is going to be this x minus 7 times this x minus 3, and we're kind of good to go. So it's going to be our answer. Now, on your paper, this one may be written wrong. I can't really remember. Some of these I messed up on. So note your paper and see if it's written correctly. If not, make it look like this. So what we're going to do now is we're going to use FOIL. In FOIL, what we pick up on is the first and the last create these pieces here. So the factors of x squared have to go in the first positions. The factors of the negative 7 have to go here. But what we need, though, is the factors of negative 7 that add up to give me this negative 6. So what we pick up on then is the factors of 7 would be 1 and 7, and that's actually it. But to get this negative 6, what has to happen is one of these is going to have to be negative, because we still need to maintain this negative 7 up here. So notice that 1 times negative 7 does give me this negative 7, and this does give me this negative 6. So these become the last terms, the 1 and the negative 7. So a positive 1 and a negative 7. Now, if I want to double check this, we can use the outer and inner to verify that we do get the middle term. So if we multiply the outer and the inner together, Notice how the outer gives me this negative 7x, and the center gives me this 1x. And combined, does that give me my middle term of this negative 6x? And we see that it does. So that would verify it. So the first x times x does give me my x squared, and 1 times negative 7, the last term is giving me my last term. But the catch is the outer and inner have to give me my middle term as we do FOIL. So if we want to factor, if we, like I said, if we want to multiply it all back out, which we just kind of did, that should give us the x squared minus the 6x minus 7. So notice how all we really got to do is use the O and I to multiply it back out. So if I want to factor x squared plus x minus 12 using FOIL, so what we did is we set up these two sets of parentheses. Now to get the x squared, we have this just x times x. But for the constant, this negative 12, there's several choices. So since there's several choices, I use big T to kind of narrow it down. But the catch is the factors of negative 12 have to give me the coefficient of the linear term, which would be a 1. So if I do this, we get 1 and 12, 2 and 6, 3 and 4, 4 and 3 is repeating. So notice how we have 3 different factor pairs. Which one has the best shot to give me this 1? It looks like this 3 and 4. But notice that this I would actually have to be negative here because we need a positive 1. So that 3 and 4 become our factor pair. So they're going to make our last term. So they're going to make the negative 3 is going to go here, and this plus 4 is going to go here. So notice how x times x gives me my x squared, and negative 3 times positive 4 gives me this negative 12. So that's been checked out. Now, to verify this all the way, we want the outer and the inner to match up with this middle term. So the outer gives me this 4x, the inner gives me this negative 3x, and if you could put those together, does that give me my 1x? And you see that it does. So that's what we mean by kind of multiplying that back out. That works for us. Let's see what our next page is. The next page kind of gets into some special situations. So if I want to multiply, if I want to factor x squared minus 25, there's all kinds of ways of doing this. A great organizer, of course, for me is 4 square. So using 4 square, the quadratic term has to go in the top left, and the constant has to go in the bottom right. What's missing is the linear term. So what I pick up on is we have this negative 25 is going to be my big T guy. But what I have to do is here, the factors of this negative 25 have to add up to what? Well, since there's not a linear term, that means its coefficient was actually a 0. So what are the factors of a negative 25 that give me a 0? Again, there's not too many factors of 25, just this 1 and 25 and this 5 and 5. And notice that to get let's see here. Make that a little bit bigger. So to make this 5 and 5 make a 0, we also need this negative 25 here. We know that one of those has got to be negative. So when we do this, we know that they have to go here and here. So the negative 5x can go here, and the 5x can go here. Now, once I build the inside correctly, and that does give me x squared minus 25, now all we have to do is build the edges. So in doing so, we know that x times x is going to give me x squared. I'm going to need a negative 5 here to get that negative 5x. I need a 5 here for 5x. And 5 times negative 5 is negative 21. I'm sorry, negative 25. So that works out for us. So the factorization of x squared minus 25 would be x plus 5 times x minus 5. Again, that order does not matter. Now, the shortcut also is a difference of squares. Notice how if you have a perfect square minus a perfect square, it's going to factor into the form a minus b times this a plus b. So notice how it's the same piece here and here, and the same piece here and here. So what has so true is there's got to be something squared. Notice how this x is squared. So we have that. What about this 25? Well, we should know that x squared minus 5 squared is the same thing as x squared minus 25, which means this is a perfect difference of squares. So what I can do is factor this into using the formula x minus 5 times this x plus 5, and that would be its factorization. And you can also use FOIL as an alternative way of doing it. So if I want to factor x squared plus 4x plus 4 using 4 squared, again, I'm going to have this x squared here, this 4 here. Again, remember the factors of the constant must give me the coefficient of the linear term. So the factors of 4 that give me 4, well, we have 1 and 4, and we have 2 and 2. And that would be it. That's repeating at that point. And notice how this 2 and 2 does work. So that allows me to rebuild the 4x as 2x and 2x as we try to take it back apart, work our way to the edges. So now I've rebuilt the inside. Now we just got to make the edges. So if we just piece the puzzle, x times x here, we need a 2 there, we need a 2 there, and 2 times 2 does give me 4. So this turns into x plus 2 times x plus 2. But that's the same thing as x plus 2 squared. So when you have the same binomial twice, I'm allowed to put a power of 2 there as that, because again, we have the same factor twice. Now, if we have a perfect square trinomial, it can also factor into this a plus b squared notation. The way it works is if I have this x squared plus this 4x plus 4, it's got to pass 3 tests to be put in this form. The first term's got to be a perfect square. Well, x is a perfect square. The last term's got to be a perfect square. Well, 2 squared is 4, so it passes. The next thing we got to do is we got to match this middle term. So what this says is multiply AB. In other words, multiply the 2 and x together. If you multiply the 2x together, and then you got to multiply that by 2. So if you multiply that by 2, that gives you this 2 and this 2x is at 4x. So we kind of see that, yeah, that's a perfect square. That's a perfect square. And when you multiply 2 times x and you multiply that by 2, that does give you this 4x. It passes those 3 tests. So that means that we can change this to then this x plus 5, I'm sorry, this x plus 2 squared. So that would be the answer to that. Okay. Now, as we move forward, we're going to get into polynomials that the coefficient is no longer going to be 1. There's actually going to be a coefficient in front of the x squared. When it is, it makes it a lot harder to do. So what we're saying here is when the quadratic term has a coefficient that isn't 1, there becomes a lot more possibilities because the coefficient of the quadratic term must multiply with the constant. So again, when we're doing full, remember this coefficient here is going to have to multiply to the constant. So that's going to be necessary when working back to factors. So our strategy is going to take that into account. So when I do 4 squared, what I'm going to do is this. Let's see if I can get where I can see it. So when I use Foursquare, the strategy starts the same. The quadratic term still goes in this top left. So 2x squared still goes there. And the constant still goes here. So place the quadratic term in the top left and the constant in the bottom right. Check, check. Our next move is to multiply the leading coefficient, the constant. So what we want to do now is we want to multiply this 2 to this 5. And that's going to create our number for big T. And our linear coefficient, we need to recognize that as well. Our linear coefficient is going to be that 11. So this strategy is very similar, except now we're going to use the factors of 10 that are going to give me this 11. So we're going to have this 1 and 10 and this 2 and 5. Which one is going to give me this 11 is going to be this 1 and 10. So 1 and 10 are going to be my little factor pair that we deal with. So what we do is we rewrite this as this 1x or x, and this 10x goes here. Again, it doesn't matter what place you put those in. Just seems like the 10x looked friendlier to that 5 and the 1x looked friendlier to this up here. So I just took that into account as I wrote that down. So it doesn't matter where they go, just see if they make sense to where you put them. So now we've made the inside using that factor pair. We now have our linear terms. The next slant is we're now going to factor the GCF from the top row. So another change is we're actually going to look at this 2x squared and this 1x, and we're going to identify what do they have in common. So the greatest common factor is just this x. So once I factor out the GCF, I now want to use, I just want to make the outer edges that fit the inside. So I want to figure out these edges that make the inside. So if I put an x here, I have to put a 2x up here. If I put an x here, I got to put a 1 there. If I've got a 2x there, I got to have a 5 here because 5 times 2x is going to be 10x. And does 5 times 1 give me this 5? It does. So now I've completed the process. The edges become the factorization. So this 2x plus 1 and this x plus 5 become my factorization. So that's using Foursquare. On your paper, this one may be wrong as well. I did make some mistakes on a few things. So let's factor 2x squared plus 5x minus 18. Again, we're going to use Foursquare and big T as a strategy. So again, I need to have my little Foursquare. Doesn't have to be perfect. And if you want to pause this and see if you can do this one without me, let's see where that takes you using Foursquare and big T. So the quadratic term stays in this top left. Oops, that needs to be a 2. So I have a 2 there. Let me see if I can clear that off there. Let's just start again. That was a little bit too messy. So I have this and this. So I have this quadratic term goes here, and the constant goes down here. Now, the catch is when you use big T, since there is a leading coefficient, you need to multiply that leading coefficient to the constant. And that's going to help us make our big T. So 2 times negative 18 is going to be then this negative 36. And then remember, we have to, these factor pairs must add up to this linear coefficient. So I'm also going to do this 5. So I have to kind of make note of that as well. So when I do my factor pairs, again, we should have a 1 and a 36 to start with. I'm going to leave the negative out. 2 and this 18. 3 and 12. 4 and 9. 5 doesn't work. 6, and there's that 6 again, so that's repeating. So those will be my factor pairs. Now notice since this is negative, one of these numbers is going to have to be negative, but I also need to get this positive 5 here. So that means this side over here really has got to be the negative side, the smaller one. The bigger number is actually going to have to be positive. And I do notice that this 4 and this negative 4 and the 9 is my winner. So I'm going to use those two terms to rewrite my middle term. And again, for some reason, that negative 4x looks better up here, and that 9 looks better down here. So I'm just moving them to those two spots. Now, the other trick is I have to now find the GCF of the first row. So if I look at a 2x squared and a negative 4x, what factors do they have in common? Well, a 2 and a 4 have a 2 in common, and an x squared and an x have an x in common. So I'm seeing a 2x is what's in common. From there, we just got to multiply the rest of it out. So I need an x there, and looks like a negative 2 there would work. I need a 9 here, and 9 times negative 2 does give me this negative 18. So that looks like we've completed the edges. So that should give us then the 2x plus 9, and then we have then this x minus 2 as my factorization. Where this leads us to is factoring by grouping. So grouping is used when you have 4 or more terms. So instead of using 4 square, what I'm going to do is model this using grouping. So again, in grouping, we're still going to need big T as a strategy. So I'm going to try to keep it out of the way of my problem. I'm going to put it over here out of the way. So I'm going to put it way over here. To get big T though, notice how there's a coefficient. We got to multiply that leading coefficient to the constant to start with. So 2 times 2 is going to be this 4. Now remember with big T, I have to add up to get that linear term, which is going to be that 5. So I need to get a 5 here as well. So from here, our factors of 4 would be 1 and 4 and 2 and 2, but that's repeating, so I'm stopping there. Which one of those has the potential of giving me my 5? I'm seeing that 1 and 4. So what way this works is when I factor by grouping, I'm going to rewrite the middle term using these as my coefficients. So I'm going to have this 2x squared, and I'm going to have plus x plus then this 4x plus this 2 then. Now it doesn't really matter where you put the x and 4x. It just looked like it would go there better. So you can kind of experiment. If you don't like it one way, switch them. It may make a difference. So we multiply the leading coefficient and the constant. 2 times 2 gave me the 4. And remember, we have to get this 5 here. So we're going to use big T, and we're going to figure out which ones adds up to that linear coefficient. We did. That 1 and 4 was my winner. So we want to rewrite the polynomial with 4 terms. So we're going to replace the linear term with that factor pair. So that's what we just did. Now our next step is going to be, we're going to group to form 2 binomials. Use parentheses. I actually like to use a box here instead. You can group it any way, but sometimes it just looks easier to do it a different way. So I'm going to draw a box around the first 2. That's going to make 1 binomial. And I'm going to draw a box around the second 2 to make the second binomial. And also I include the operation there as well. So from there, I want to factor the GCF from each one of these binomials. So I look at this, and I look at what is my GCF? What I'm seeing is an x, and that leaves me a 2x, and I have to leave a 1 there because you can't throw that out because remember, you have to multiply this back together to get this here. So x times 2x does give me 2x squared. X times 1 does give me that x. So the 1 stays there. When I look at these two terms, I see that they have a 2 in common. And since it's positive, I put a plus 2 out here. And then I have a 2x plus 1 left over. Notice how again when the 2 came out, we use a 1 as a spot there in multiplication. 2 times 1 needs to be there. So from there, we factor the GCF from each binomial. Now we want to factor the GCF binomial. Notice that this 2x plus 1 and this 2x plus 1, they're in common. So that binomial now comes out in front. That factor comes out in front, that 2x plus 1. And then what's left becomes our second set of parentheses. So that x plus 2 is what we pull out on the end. That's what's left over. And so this should be a binomial times binomial. It checks out. That's factoring by grouping. So another example. I think I wrote this one down wrong. I think this actually should be here should actually be a minus 5 here, not a plus 5. So sorry about that. So that's what we should have in our notes is 3x squared minus 2x plus 5. So let's look at this example. So again, if I want to do factoring by grouping, we want to use big T. But the way big T works is since we have a leading coefficient, we multiply the leading coefficient to that negative 5. In doing so, we get this negative 15 as our number. And then our linear coefficient is that negative 2. So what we're first starting out is we're trying to figure out these factor pairs, but they have to add up to give me this negative 2. So again, if you want to pause the video and see where you can go with this problem, that'd be a good idea. So I have now 1 and 15 is the first factor pair, and we have 2 doesn't work, 3 and 5 does. 3 and 5, that looks good. So let me see if I can erase that. Yeah, I can get that out of there. So looks a little bit cleaner. But notice I need a negative 2 and I need a negative 15. This isn't working for the time being. But since I need a negative, I know one of these has got to be negative because in multiplication, to get a negative, one has to be negative. And to add, the bigger number has got to be negative. So if I do that, we pick up on that this 3 and this negative 5 become what make this true. So as we follow our steps, we now want to rewrite the middle term using those. If possible, the negative we always want to put first and the positive in the second position. But here I'm going to go ahead and do it the other way and show you what happens because it really doesn't matter. So I have this 3x squared plus this 3x minus this 5x. So I'm going to rewrite the middle term using those two coefficients. And then we have this minus 5 on the end. So I've now broken it apart into 5 terms. So now we want to group it as binomials. So I'm going to have this binomial. And when I do this binomial, we have that going on. So our next step is to find the GCF between these two terms. So what I'm seeing is there's a 3x in common there, which leaves me an x. And again, since that all came out, we use a 1 to keep it in place. Because you remember when you multiply this back through it, it has to represent that. And it does now. Now notice how there's a negative and a negative here. Anytime this term is negative, anytime this term here is negative, what we want to do is go ahead and factor the negative out. And they also have a 5 in common. So what I'm actually going to do is pull out a negative 5 here. Remember when you pull the negative out, both signs have to change. So that x does remain, But since I pulled that 5 out, remember 5 divided by 5 is still going to be that 1, but it's going to be a plus 1. So now we factored out the GCF of each binomial. We're left with, I'm sorry, we're now going to try to factor out the GCF binomial. That's our last step. So the GCF binomial is the binomial that they have in common. So notice how these two terms have that x plus 1 in common. So I want to factor that out so that x plus 1 comes out, and then I'm left within this 3x minus 5 as my second binomial. So I have a binomial times a binomial. So if I do this last one by grouping, again, I like to use big T as a starting point. So notice how there's a leading coefficient. So to do grouping, our first move is to multiply the 3 times the 4. That's a 12. But remember, we're going to be creating factor pairs that have to add up to this -8. So again, if you want to pause this video and see if you can get this going. So I have a 1 and a 12, a 2 and a 6, and a 3 and a 4, and a 4 and a 3. So there's my factors of 12, but also have to get a -8. For it to be a -8, and this has to be a positive 12, both sides actually have to be negative. Because we know that a negative times a negative is a positive, and a negative plus a negative is actually a negative. Which one of those gives me that -8? I'm seeing the -2 and the -6. So I'm going to rewrite the middle term using that. So I'm going to have this 3x squared minus 2x minus 6x plus 4. My next step then is to group. So I'm going to group the first two and the second two. So now I got this binomial and this binomial here. Now remember, when I use the circle method, this is understood to be addition as well. So I'm looking for a GCF between these two terms, and I'm seeing there is an x. And that leaves me this 3x minus 2. Actually, yeah, 3x minus 2. Now, when I look at this, I have the 6 and 4. A 6 and 4 looks like it has a 2, but notice how there's a negative here. I want to go ahead and pull that negative out as well. So I'll pull actually a -2 out. In doing so, what's in the parentheses will have to change signs. So this -6x, when I pull that -2 out, is going to turn into a 3x. And notice -2 times 3x is -6x. That checks out. And when you pull a -2 out of this, that sign has to also change from a positive to a negative. And again, notice that -2 times -2 does give me a positive 4, so it does check out. What's also nice is I do have that greatest common factor binomial. So that's going to get pulled out in front. And the remaining pieces become the second binomial. So that leaves me this x minus 2 as my second binomial. Okay. So now we're on the home stretch here. This page here basically just highlights the strategies before us. So in factoring polynomials, step 1, always look for the GCF. It could look like a monomial. Step 2, check for special products if you feel comfortable. This is a shortcut. So remember, if it's a difference of squares, the only way it's going to factor is this a minus b and this a plus b. If it's a perfect square trinomial, remember that's one that you have to do the 3-step test. And if it passes all 3 tests, that gives you this a plus b squared. We also talked about factoring second degree trinomials where the coefficient was a 1 here. Remember, when it looked like this, all we really had to do is focus on the constant. So you can use 4 square and big T, or you can just use FOIL and big T. Like big T is a good way to organize the factors of the constant to add up to give you this linear coefficient. Now remember though, if it's a second degree trinomial where there is a coefficient that's not 1 in front, remember you got to multiply the A times the C. In other words, the leading coefficient and the constant first. Then you can go into big T. So you can use, if you use 4 square and big T, you have those steps to go through. But also we have factoring by grouping if you want. Now remember, if it already has 4 terms, you're going to be factor by grouping. Also, if the factoring strategies don't work, it could be prime. Therefore, it may not even be factorable. So if it fails all tests, if you see me do a few of these in class where these actually crashed. So that concludes my lesson on factoring polynomials. So see if we can stop the recording.